Okay? So, before explaining the Bellman equation, or put it another way, I'm going to explain the Bellman equation using a timeline. Okay, so this timeline looks like this. Remember, this person, if he's working, he's receiving the wage, or he's counting this wage at the end of the period. And the separation, or whether it's separated, is also counted at the end of each period. Okay, so this is period 0. This is period 1. This means the starting point of period 1. Okay, so take any period actually, but let's say period 0. If this person is working and has a wage offer, W, what happened? At the end of the period, this person will receive U of W. Because this period he is working and the wage offer is W, and his consumption is going to be W. So he enjoy utility U of W, right? And there is a chance that this person is going to be separated. That's probability S. If he or she is separated, then from that point on, from that point all the way until the end of the infinity many period, his value is going to be VU. That's how we define it. We define it to be VU. Okay. And there's a chance that this person is not going to be separated. 1 minus S. If he or she is not going to be separated, then he or she will receive what? He will keep receiving VE of W. You might feel a little bit confused right now, because I defined VEW to be basically like this. You are starting from time 0, and you're receiving the wage offer W, and the total amount of value you get, right? But now, it seems like this person, although he's also getting the wage offer W, but he's only getting the wage offer for 1 period less, right? He didn't receive, this is counting starting from period 1, not period 0, right? But why do I still use the VE of W? Why? There's 1 period difference. Why do I use the same phrase, VE of W? I don't know if you guys have learned these tricks in maybe junior high or high school. So you might see this before, okay? 3, there's a sequence. 3 to the, half to the power of 1 plus half to the power of 2 plus half to the power of 3 plus blah, blah, blah. Infinity, many, many terms. Okay. And there's a trick to do this, is you let A equal this. and you say 2a is what? 2a is 1 plus this. Plus right? And you say that this is exactly like this. So this part is A. Right? And then you'll find, oh, great. You have this. And you cross out the A, and you'll find that A is actually 1. Right? Here, it also feels like there's a 1 period difference. But why can I do this? It's the same trick. Well, the trick here is the same, right? Although there's a 1 period difference, but from the time point of period 0 or period 1, the common period are both infinitely many periods. Infinity plus 1 or minus 1 are still infinity. We don't distinguish them in math. That's why I still call it VE of W. I'm still receiving. So one term is I'm standing at time point 0. I'm looking ahead. I'm saying, oh, now I'm receiving a wage W. What's my total value over this infinitely many period? The other term is now I'm standing at time point 1. I'm looking ahead. Also infinitely many period. What is the value of me already getting a job wage offer equal W? It's the same thing. Okay? Understand what I'm saying? This is the key, the whole key to the whole model. So if you don't understand this, if you think I'm just jibber-jash, don't know what I'm talking about, I strongly suggest you raise your hand right now. Even just to stop me, even if you don't have any question, if you just don't understand what I'm saying, please raise your hand. Okay, I can assure you, this will be tested in the midterm. Okay, and I can also tell you last year it was a disaster. People also tell me that they understand, but in the midterm, less than 10% of the students made that question correctly. Okay, so this term, this is after 1 period has left, has gone. What's the value I get at the end of that period? And counted all the period ahead. But I already know that term, because this thing, this is this. If I discounted 1 period back, that is, standing at here, I discounted back to period 0, which means I need to divide it by 1 over times 1 over 1 plus r. Then that is by definition VE of W. Right? That's the value I receive for all the period ahead. So the tricks here is I first define the VE of W, and I use another way to define this VE of W. I use one period ahead of way to define that. It's similar to the tricks I did for the infinite sequence. I move one period ahead and redefine it, and I make the two definitions equal to each other. That's basically the Bellman equation. So VEW actually equal to 1 over 1 plus R times this UW plus SVU plus 1 minus S times VE of W. Depending on your definition of the timing, for example, if you let the person receive the wage at the beginning of the period, then this term won't be discounted because this is the beginning of the period consumption. Then this term will come out. It will be UW plus the discounted part, these two terms. But that model will still work, but it's gonna be more complicated. So the way I'm doing this right now, actually this one is not in the main textbook, this is in the appendix. Okay, appendix for chapter 6. So in this version of the model, I make the U of W inside the bracket. I assume that this person received the consumption afterwards, after one period. Okay. And after we have this Bellman equation, we can move this 1 plus R to here. Then we will have 1 plus R times VE of W, right? And after I move out this bracket doesn't really matter. And you see here I have 1 times VE of W. Here I also have 1 times VE of W. So you can cross out both the left-hand side and the right-hand side. So here what I left is R times VE of W. The U of W is still there. And because I moved this one out, then right now these two terms both have this S. So I can move the S out and make it S times VU minus VE of W. Well, actually that's not necessary, but doesn't really need to do so. You can give it back. But either way, I'm gonna pull the VE of W together. So I'm actually gonna pull this minus S times VE of W to here. So it become a positive 1, right? So it's gonna be R plus S times VE of W. And I move the R plus S to the other side, right here. That's the R plus S. And what I left here is VU of W plus S times VU. Get it? Okay, keep this in mind. This is a really important equation I'm gonna use later on. So at least I know VE of W is a function of U of W plus S times VU divided by R plus S. And since we have this is the same equation from last page. We know what? because R, S, S, and the VU here, they're, I mean, I haven't proved that VU is really a constant, but think of it as a constant because it's not depending on W at least. Okay? Because you're unemployed, you're not related to that wage offer. You're not receiving any wage offer. It cannot be related to wage. So these are not related to W. So when W changed, the only thing that changed here is the U of W. So U of W, we assume that it is strictly increasing, continuous, and strictly concave. Then VE of W is going to be also strictly increasing, continuous, and strictly concave. Right? Because whatever this function has in terms of characteristic, it will carry over to this function. Okay? And let's define something called the W star. Actually, this W star is called the reservation wage. Okay, reservation wage. Okay, what is the reservation wage? It is defined such that the worker is going to accept any wage offer greater than or equal to W star, but reject anything that's lower than that wage. This should be straightforward. There should be a cutoff, right? A cutoff where if the wage is high enough, I will accept the job. If the wage is low enough, too low, I will not accept the job. Remember here, there's only two things. Either I work or I don't work. I accept the job or do not accept. It doesn't have that feature like I told you before that the labor supply can be backward bended. Right? You can, maybe the wage is too high, I decided to work less. Here, the working, whether you work is a binary variable. You either work or not. So if you work at a higher wage, then the even higher wage you should work as well. You shouldn't be the case that the wage now is 20, you work, but in 30 you don't work. And if you don't work at wage 15, then you shouldn't work at wage 14 as well. Right? So there should be a cutoff. That cutoff is the W star. So that it is defined so that when you receive a W star, you are indifferent between whether you want to wait or work or not. Okay. By that definition, VE of W star is going to equal to VU. That's the indifferent part that I just said. Because this person is indifferent between work or not work. Right? Okay? Okay. And then, because I know the function form of VE of W, right? So VE of W star is also this, which is this. U of W star plus S times VU divided by R plus S. Okay? And if you have VU equal this thing, and you can move the R plus S here, you will have R plus S times VU equal U of W star times SVU. The SVU is crossed out, and the R can go back here. So VU is going to become U of W star divided by R. Remember, R is the discount rate. W star is a constant that satisfies the definition I just described. U of W star is therefore also a constant. Here I show you VU is actually a constant. Okay. It depends on the reservation wage. But that reservation wage, if it is fixed, then it is fixed. So far, okay? The difficult part hasn't came yet. So if you have any questions, now is really a good time. Okay? No? Okay. Okay. Another way to look at this function. VE of W. We want to see when S, the separation probability is changing, what happened to VE of W. So we do a simple differentiation against it. And this is quotation rule. Okay, so you differentiate this with respect to S, but not this, minus you don't differentiate this, but differentiate this. And then divide it by the square of this, which gives you this. Okay, this is, undergrad calculus. I'm not going to go to detail. Also the easy part of the undergrad calculus. And you sort of rearrange it, you will see that the SVU is crossed out. So you actually have RVU minus U of W. And I can show you that this is actually less than 0. Why? Because from last page, I know that VU equal to UW star divided by R, right? And that is going to be less than U of W divided by R for any W that's greater than W star. So that means it is for any W that will let this person be employed. Any employed worker will have a wage that's greater than W star, right? By definition. So which means it must be the case that W is greater than W star for this W. So since VU is less than U of W divided by R, then RVU is less than U of W. So this term is negative. And this must be positive. So the whole thing is going to be negative. So what we know? We know that VE of W decreases with the separation rate S. That means when separation rate is higher, this VEW is lower, which makes sense, right? This is the value for you to have a job that has a wage W. But if the separation rate is higher, that means even you have this job, there's a chance that you'll be fired. And this fire probability is higher, then the value for you to possess this job is going to be lower. Right? Now we turn to the VU. Okay. I know I have decided that calculate the VU for you, but now let's look at the VU from another perspective to go to the definition of VU. Based on the definition of VU, what is VU? That's what's the value for you to be not employed, right? So also, after one period, because this period you are unemployed, you will receive a unemployment insurance. That's going to be B. So you will receive U of B. That's the consumption utility you get for this period. And there's a 1 minus P chance that you won't get any job offer during this period. If you don't have any job offer, what happened? You keep being unemployed, right? So with probability 1 minus P, you are also unemployed. You're still unemployed. So that's what you get. Okay. And with probability P, you will actually get a job offer. But remember, this job offer, it's not always the case that you will accept the job offer. The job offer needs to be good enough for you to accept it, right? So here, what I'm going to do is, this looks complicated term, is simply take a expectation of the job offer or the value that I will receive for some job offer. This is basically expected value of VE of W. Because I'm not sure what kind of offer I will receive. I need to take it in expectation. And because this is a continuous variable, so the expectation takes the form of an integral. So I take the integral over the period, over the range of 0 to W1. Remember, that's the lower bound and upper bound of the wage offer that you will get. Okay, this is just the PDF, the probability density function of the big F of W. So if you don't remember Fx of Fx dx, that's basically expectation of x. So given that f of x is x density function. So this is what I'm doing here. And the function here looks a bit weird. It is a max function, max over VU and VE of W. The reason why it looks like this is because I'm going to receive, it's possible that I'm going to receive different job offer, right? It's not that all job offer I will take it. Only when VEW is greater than or equal to VU, I will accept it. Otherwise, I would turn down the job and keep taking VU. VU is better for me, I would take VU. If VEW is better for me, I would take VE of W. That's why I'm taking a max here. I can choose between these two and always pick the max, basically. You see what I'm doing here? Okay, so that's why I'm taking a max. So, like I said, this is basically taking an expectation of the value of the VE of W. With probability P, I'm going to get that, right? And similar trick, I discount it back for one period. And that thing, the whole thing must equal to VU. That's the same Bellman equation trick I have for the employed people. Okay. And Again, you move this 1 plus r to here. What you get will become r times vu equals u of b plus p times this. Okay, here what changed is that I actually have a v, so 1 plus r times over here. So I have 1 plus r times vu on the left hand side, right? And I move 1 vu to the right hand side. So it becomes minus 1 vu. Okay. And that minus will cancel out this one. But I still have minus p times the vu. So if I take the common product of p out, then the minus 1 times vu can go inside the integral. If there's a minus 1 vu inside the integral, the max function, this one will minus vu, this one also minus vu. And vu minus vu is just 0. Ve of w minus vu become this. Ve of w minus vu. And this whole term disappear, and I still have the u of b. That's why I have u of b plus the whole thing. The key is how to get this. Okay? And then this actually become easier. Okay. I know, as a matter of fact, when will VEW greater than VU or equal to VU? That's VE of W star when W equal W star, right? So I know for lower wage, this person is just gonna ignore. That means for wage between 0 and W star, the 0 is going to be bigger than this term. I'm taking max between these two terms. But for the range between 0 and W star, this term win. So the whole integral is going to be 0. Right? So for those parts, the integral doesn't really matter, basically. So what I do is I move the lower bound to W star, then the max can go out, can disappear. What I left here is VE of W minus VU. Because after I constrain on the range for W star to W1, for this whole range, I know as a matter of fact, VEW is greater than VU. So VEW minus VU is positive. And if it is positive, it's always going to be greater than 0 by definition. So the max function can go out. Okay, the trick is, just by the definition of integral and the max function and the definition of W star. Okay, and remember VEW is what? R plus S over U of W minus SVU, right? Plus SVU, sorry. I have the VE of W here, right? I insert these things, or I should write it this way. I insert the whole thing inside. Then it become, what's in the integral become r plus s over, u of w minus r times vu over r plus s. Okay? This one is just that I inserted. It's not too complicated. Okay. And also because I know r vu is u of w star. So this one is actually u of w star. I can replace that with u of w star. And I take the r plus s out. I make it here because that's going to be a constant anyway. And then this is what your TA help you in the second week. Okay, you do a integral by parts. Then you will get what's inside will become 1 minus f of w times u plum of w. Okay. To make it clear, this is the detail step. So this is the original term. When you do an integral by part, what happens is you sort of assume this is something that's already taking differentiation. This one hasn't been take differentiation, for example. And the term you put here would be this term plus this term before differentiation. That's going to be capital F of W. And I hope you know what this means. That means insert the W1 and W star and take the difference. And minus what? Minus this one before the differentiation and this one after the differentiation. So this is f of w before the integration, and this is these things differentiated with respect to w. U of w star is a constant, so there's no differentiation there. So basically what you left is u plum of w. U plum of w is dw du of w, the same thing. And if you actually insert the w1 and w star inside, remember f of w1 is going to be 1 by definition, because that's the CDF. CDF with the upper bound will be 1. Okay. So the first term would be u of w1 minus u of w star. And then the second term, if you insert w star inside here, then this term becomes 0. So the second term is 0. So what you get is u of w1 minus u of w star. Minus this. This one doesn't change. And the last trick here is that observe that u of w1 minus u of w star is actually an integral equal to an integral of from w star to w1, and inside is u plum of w dw. If you don't believe me, just do the integral back and you see they equal each other. And then right now I have the same range of integral and I can combine the term inside. Then what I get is this. 1 minus f of w times u plum of w. Okay? Now, since I have this whole thing, this one is this one. Okay? This one is that one. Then what I can do is I can simply divide this r here and get UB divided by r and this constant times this whole thing. And this one, I don't need to do the differentiation. I can easily observe that VU is increasing with the unemployment benefit B. If B is higher, the only thing that changes here, that this is going to be the higher. So VU is going to be higher. And also increase with P when the probability of getting a job offer is higher. VU is going to be higher. And it is decreasing with R and S because R also only appears here if it has a higher R, the whole thing is going to be decreased. Same thing with S. Again, VU, when I say it is a constant, what I mean is it is a constant with respect to W. Okay, you can see W here, right? But remember, this is something that I'm going to integral out. So at the end, there's no W. But VU still depends on something. It depends on B, P, R, and S. And let's come back to the reservation wage. Okay. Recall that, so U of W star equals RVU. That's what I get from the first part of the lecture. If you don't remember, I have something there like this. So U of W star equals RVU, and RVU equals this whole thing. Right? So RVU is this. And you see that the left-hand side is obviously increasing in W star. Right? And the right-hand side, I mean, the only W star is here, right? So if you increase W star, that means the part that you do the integral, the range you do the integral is a smaller range. If the integral range is smaller and everything inside is positive, this is positive, right? Because the utility function is a increasing function. So the derivative is positive. And this is 1 minus the CDF. It must be positive because the CDF is going to be between 0 and 1. So the whole thing is positive. So if you integral a function that is a positive and the integral range becomes smaller, it means the whole thing has to be smaller. At best, it doesn't change if the function is 0. So what it means is if you increase W star, this right-hand side is actually decreasing. So if this is increasing with W star, this is decreasing with W star. We can easily show that the W star can be uniquely pinned down. Right? This is like supply demand. One side, when the W star is higher, it is higher. The other side, if the W star is higher, it is lower. Then it must have only one cross point. So, like I said, it should be intuitive that W star is unique, but I mean, there's a way to prove it. And after we actually pin down, we sort of, put it this way, we sort of assume that there is a W star when I construct the model for VE of W and for the VU. But this is how I can actually pin down the exact number of that W star to calculate that W star. Okay. And after I obtain this W star, then I plug that back into the utility function. I can get the VU, then the VU become a constant, given B, R, S, and P, those constant network. So on the textbook, the main text, it is actually a much simpler model. It will give you a graph like this. Okay. It says that VEW and the VU will cross at the reservation wage, basically. But another way to look at this is U of W. U of W is also an increasing function. Remember? Concave, increasing, continuous. And W, for any W level, VU is a constant. And when will the VU, or you put this as RVU, doesn't really matter. Okay. When will RVU meet the U of W? That's when W equal W star. Okay?